Okay, thank you. It's a lot of fun to be here talking to so many interested people. So the scientific quest to understand the fundamental laws of nature has been ongoing for centuries or even millennia. And this lecture, I'm going to describe some of our ongoing confusion, the progress, the excitement about the edge of our knowledge. And interestingly, the edge of our knowledge, the frontier of what we currently understand, that is, the beginning of the things that we don't understand, a lot of it coincides with the edge of the physical universe, which are horizons which may surround a black hole or a different region of the universe. Now, we understand an amazing amount about the universe that we live in. So we understand in a very precise way how the lunch that I ate has been metabolized, turned into energy that enables me to move around and to give this lecture. We understand how we can send a rocket off the Earth and we can predict its precise trajectory in the solar system, and when it arrives on Mars to incredible accuracy. At the same time, and it's kind of, when you think about it, it's an amazing thing that, tens or thousands of years ago, none of this was understood and none of it was obvious. And it's an amazing thing that the human mind can learn so many completely inobvious things about the physical world around us. So while we have learned and understood a truly spectacular amount, at the same time, there are very basic questions that a 3-year-old can ask that we are completely clueless as to the answers to. For example, how did the universe begin? Why are there 3 space dimensions? Many such questions. They go on and on. But the interesting questions, I think, are the ones that we are beginning to have a clue how to answer. And those are the ones that are the most interesting to a scientist. And so how do we figure out which questions we want to think about? Well, if we want to try to learn about the physical universe around us, the best thing that we can hope for is a contradiction. So this story repeats itself many times in the history of physics, and a famous one was Einstein, who was he came up with the following thought experiment. He says, what happens if I hold a mirror in front of my face and run faster and faster? As I go faster and faster, the speed of light had already been measured then at 186,000 miles per second. What will happen if I'm going so fast that the light that leaves my body can't reach the mirror and come back to my face? Will my image disappear? What am I going to see in this mirror? And at that time, there were 2 ways of trying to answer the question. One given by Maxwell and the Maxwell equations, and the other given by Galileo and Newton according to the symmetries of Galileo and Newton. If he used the Maxwell equation, he would conclude that the image would disappear, but according to Galileo and Newton, all inertial reference frames are the same, so nothing should happen. And these were not consistent. So he had 2 ways of trying to analyze the same situation that gave different answers. That's a contradiction. And that really bothered him. Now, of course, Einstein was a very talented fellow, but he couldn't actually run faster than the speed of light to do this experiment, but there was no limits to what he could do in his mind. And he came up just from this tiny little contradiction that the everyday person was not very worried about. He came up with a really shocking conclusion, that nothing can travel faster than the speed of light. That the thought experiment was essentially flawed because nothing could go faster than the speed of light. And that shocking conclusion transformed our view of space and time. It led to practically all of 20th century technology, atomic power, and it changed the world, the little thought experiment. And all such revolutions in physics, if you look at them, not most of them, all of them, are seeded by some kind of contradiction of this type. So here is a cartoon of what has been happening in physics over, I guess this is going back more than 400 centuries. So we had the laws of thermodynamics, which actually will appear later in this talk. The laws of thermodynamics tell you if you have a pot of water and how you put a burner under it, you put it in a microwave or something, how much energy you have to put in order to heat it up. And those were exhaustively studied in the 19th century. Then, at the end of the 19th century, electromagnetism was discovered. That is, the electric and the magnetic forces were found to be part of the same object. And so one could try to apply thermodynamic reasoning. You could ask the question, what happens if you heat up the electromagnetic field? Well, if you used Maxwell's theory of electromagnetism and Boltzmann's theory of thermodynamics, you would discover that there would be an explosion. And that was a contradiction because people had tried it and there was no explosion. And resolving that explosion, you had to give some discreteness to the electromagnetic field, and that was quantum mechanics, which said that things have a fuzzy nature. Similarly, in Einstein's theory of special relativity, nothing can travel faster than the speed of light, as we just discussed a moment ago. But in Newton's laws of gravity, the gravitational force is instantaneously transmitted. If the sun moves by an inch, the gravitational field at Pluto changes instantaneously. And so the signal is transmitted everywhere, according to Newton, throughout the universe instantaneously, certainly faster than the speed of light. That was a contradiction, bothered Einstein, and to solve it, you needed something really dramatically new, Einstein's general theory of relativity. Now, all of this culminated in the 20th century in two great bodies of knowledge, one of which I'll call quantum field theory, which is the synthesis of quantum mechanics and special relativity, and it's consistent with thermodynamics, and it includes the Standard Model, the Higgs boson. So there's one huge world here called quantum field theory, which came more or less to its modern form 40 years ago. And then there's also Einstein's theory of general relativity. And the subject of this talk is that these two fields are contradictory. They're not compatible. And I think everybody believes, every physicist believes, that when we understand how to reconcile general relativity with quantum mechanics, that the result, the new theory that we will need, in order to reconcile those will have implications for the way we think about the universe around us that are at least as revolutionary as the implications of quantum mechanics and relativity themselves. So it's a very exciting problem. It's a big problem. It's a problem which is so big, we've been working on it, active work on it has been going on. It was understood 50 years ago, but active work has been going on for maybe 30 years. It's so big that we shouldn't expect to solve it on a 5-year, 10-point plan, but it's not so big that we can't think about it in a very concrete way. And so it sits at the interesting edge of our knowledge. And string theory and the related web of ideas is the leading candidate for how these things might come together, though it's far from being confirmed. So I'm going to first explain the nature of this contradiction between quantum mechanics and general relativity, and then talk a little bit about string theory, and I'll end up talking a lot about black holes, which in a surprising way have come to sit in center stage in these investigations. So according to Einstein's theory of general relativity, the basic idea, which I'm giving you in a one-page cartoon here, is number one, space is curved. It's not flat. And number two, if you have a mass in the middle of the space, if you put a mass in the space, the surrounding space-time becomes curved. And it's a pretty good analogy. The trampoline analogy is actually pretty accurate. If you put a bowling ball in the middle of a trampoline, it will sag down. Now, if you then roll a ball, or if you put an ant on a trampoline and instruct it to move in a straight line, that is, put one foot ahead of the other, it will actually walk in what looks like a curve. The ant, who doesn't see the whole trampoline, will think it's continuing to put one foot ahead of another and move in a straight line, but in fact, the motion will look as if it's a curve. And so, in fact, gravity is everything. When there are only gravitational forces, everything moves in a straight line in that sense. But it's a straight line in a curved space. And if we don't realize that space is curved, we will think that it's moving in a curved line. And so gravity is really an illusion caused by the curvature of space. That's general relativity. What is quantum mechanics? Well, quantum mechanics is, the essence of quantum mechanics is captured by the uncertainty principle. And the uncertainty principle of quantum mechanics says that positions and velocities do not have simultaneous absolute meaning. In other words, it may look like I'm standing perfectly motionless, but according to quantum mechanics, that's impossible. If my position is very well defined, my velocity, the uncertainty in my position, if the center of mass of my position is very well defined, the uncertainty in my position must be very large. So in fact, things cannot be at one point with a very definite velocity. There's some uncertainty if one tries to describe both the position and velocity of an object with arbitrary accuracy. And Planck's constant, now for ordinary objects, this uncertainty is very small, but Planck's constant tells us governs how big it is. Okay, so now I've already told you enough to understand why it's problematic to put together quantum mechanics and general relativity. So space-time itself is the medium that carries the gravitational force. According to Einstein's theory of general relativity, the dynamical object is space-time itself. Before Einstein, space-time was viewed as it's like a fixed blackboard on which everything can be written. It's the arena on which all the other forces and particles carry out their interactions. But now, all of a sudden, according to Einstein, the blackboard itself is starting to wiggle, which makes it hard to write on. We no longer have a fixed reference that we can describe everything relative to. So the uncertainty principle says that everything must be uncertain, and that must somehow include space and time. But making precise sense of those words is difficult, both conceptually, and this conceptual problem translates into mathematical inconsistencies and physical paradoxes. So this is the conceptual picture, but then if we actually try to write down the equations, we find that this problem appears in the equations. So let me tell you, there's two aspects of the inconsistency, one which was first noted by Pauli in the 1950s. So quantum field theory, which is the synthesis of special relativity, not general relativity, and quantum mechanics, governed much of 20th century physics. A lot of attention was paid to it. I counted them the other day. There were 43 Nobel Prizes that have been given for quantum field theory in one form or another. It's the most quantum electrodynamics, which is the version of quantum field theory that applies to electrons, electromagnetic force, has been measured to 16 decimal places. It's the most accurately measured theory in the history of human thought. Spectacularly successful. And it's a kind of machine where you take a classical theory of the type that was studied before the advent of quantum mechanics, and you adapt it and you turn it into a quantum theory. Out the other end, you get a quantum theory. Now, people thought, okay, it worked for the weak force, worked for the strong force, worked for the electromagnetic force, worked for the neutrino, the muon, the electron, worked for everybody in town. Let's try to use it for gravity. Well, they tried to use it for gravity already in the 1950s, and it didn't work. You just got garbage out the other end. Now, so what you need is a new attachment for the machine. And in the 70s, we found a new attachment. It was called string theory. And if you modify this machine in this very particular way, you can make sense of gravity with quantum mechanics. It's not quite quantum field theory. But we don't know if this attachment is actually the one ordered by nature. We'll come back to string theory later. But for this reason, this incompatibility of quantum mechanics and general relativity, the physics course in our graduate and undergraduate sequence are not mutually consistent. You will get different answers to certain questions depending on which courses you take your formula from if you are talking about a problem that involves both quantum mechanics and general relativity. Now, you can get the same answer if you use string theory, but that has a higher number here. Okay, but we don't know if it's the answer that corresponds to what's seen in nature. Now, this is a kind of technical problem. You try to put the equations together and they don't work, but there's a much more physical version of this incompatibility, which Stephen Hawking and Jacob Bekenstein discovered in 1974, and that is where a lot of the attention of this field has turned, and that's in the context of black holes. So now let me tell you what a black hole is. So on the moon, the escape velocity, if you shoot a rocket which has no fuel in it, you just launch it, a fuel-less rocket, off the surface of the moon, if it's going greater than 2 kilometers per second, it will escape. If it's going less than 2 kilometers per second, it will go up, will crash back down onto the moon. On the Earth, it's 11 kilometers per second. The Earth is bigger, the force of gravity is stronger, so you have to start off a little faster. Now, we can imagine an object with so much mass that the escape velocity becomes equal to the speed of light. And then nothing can get out. Even if you send a light ray up, it will get dragged back into this object. And that's called a black hole. Nothing can get out of a black hole, not even light. Now, black holes were discovered as an implication of the Einstein equation by Schwarzschild in 1916. And they were so strange and confusing that people thought that they just couldn't exist. And even Einstein himself didn't believe they exist. And this is a quote from Einstein in 1939. This is whatever, 33 years after the discovery of the Schwarzschild solution, in which he says that black holes don't exist and gives a reason for it. And I teach general relativity now, and if somebody wrote this on exam, I would give them an F. Well, I mean, we understand a lot more about general relativity now than we did then. Most graduate students today understand general relativity better than Einstein did, and certainly understand black holes better than Einstein did. There is progress in understanding things. But I'm telling you this as an indicator of how incredibly difficult it was to understand what a black hole is. And it actually took 60 years. And this, that is a really long time. You might not be surprised if it takes 60 years to build an experiment, to do a measurement, and to discover some new things. But it took 60 years to understand equations that were written down in a completely mathematically precise form. And now we understand a lot after the 60 years. So I'm saying by the mid-70s, we understood the classical properties of black holes before we included quantum mechanics. And not only that, we now, we see them in the sky, and we believe that, for example, at this moment, there's a big million-mile-across black hole, Sagittarius A star, in the center of our galaxy, around which this whole room is orbiting as we speak. So not only do these things exist, but they're all over the place. Now, one of the things that bothered Einstein about a black hole is that it means that it's an edge. There's a kind of edge of space. What happens in the general, I told you that if you put too much mass in one place, that light can't get out, but you can ask what does the geometry look like? And it basically looks like a hole in space. And there's nothing inside a black hole. And when I say nothing, I really mean nothing. I don't mean empty space. There's not even empty space there. Space itself comes to an end. And you can't write anything. You know, if you have a collection of black holes and you want to keep them separate, you want to call them, say, Fred and George and Susan, you can't write the names on the surface of the black hole because the writing will just fall in and dissolve into nothingness. So they are very strange and disturbing objects. And the fact that there's nothing in there, in a sense, means that they are the simplest objects in the universe. They have no features whatsoever. That is the characterization of black holes that comes out of the Einstein equations. So after 60 years of hard work by physicists and mathematicians, we reached some kind of understanding of what a black hole is if you ignore quantum mechanics. And then in 1974, in a very beautiful paper, very beautiful and ultimately very simple paper, Hawking asked the question, well, what does quantum mechanics have to say about black holes? How is the story different? And he showed that, in fact, they radiate quantum mechanically. Stuff comes out of, radiation appears to come out of a black hole, and he gave a very explicit formula for the temperature of the radiation that comes out. It's what's called black body radiation, characteristic radiation emitted by a hot body. And the temperature, it's called, the H is for Hawking here, is Planck's constant divided by 8 times pi times Newton's constant times the mass of the black hole. And this is a law, a thermodynamic law, which relates the temperature of a black hole to its size. Now, it's very puzzling to understand how radiation can come out of a hole of nothing, but Hawking argued persuasively that it must be so, and the argument was so simple and elegant that nobody has really questioned whether it is so. People could question it. They've questioned everything else, but I don't hear people wondering if it really is so because the argument is just so incredibly simple. Now, this relationship between the temperature of the black hole and the mass of a black hole is a kind of relationship which, it's called a thermodynamic relationship, which has been studied for several centuries. So, for example, if you have a glass of water at room temperature at 70 degrees and you want to heat it up to 100 degrees, you can ask, how much energy do I have to put into it? If I put it on the stove, how much energy from the gas burner or in a microwave? And there's relationships, and these are called thermodynamic relationships. And in one of the really, so these thermodynamic relationships were studied in the laboratory in the early part of the 19th century. And in one of the really the most beautiful developments in the history of scientific thought, Boltzmann showed that if everything was made of molecules, molecules was a very controversial, the theory of molecules was very controversial at this point in the 19th century, but he assumed it. He said that all the thermodynamic laws could follow from a statistical analysis of the properties of molecules. For example, you have a bunch of molecules, say water molecules or vapor molecules bouncing around in a box. Statistically, it's extremely unlikely if there's typically a liter of some gas would have of the order of a trillion, trillion, trillion molecules, statistically unlikely that all of them are at one edge of the box, even though it's not logically impossible. Statistically, they're going to be evenly distributed around the box. And just from analyzing these properties, you could deduce these thermodynamic laws. And in inducing the thermodynamic laws, an important ingredient is the so-called entropy, or the logarithm of the number of possible configurations of all the molecules in the box. And that's a measure of the complexity of the system, right? If there's only one molecule in the box, it's not very complex. The number of possible configurations is just labeled by the position of that molecule. A lot of molecules, it becomes very complicated, and you have to give a lot of positions, and this entropy gets big. So you can think of it as a measure of the complexity of the system. You can also think of it as a measurement of the information storage capacity of the system. Now, applying Boltzmann's reasoning to the thermodynamic laws of black holes ascribes a number of microstates to the black holes. In other words, this temperature relationship that Hawking found between the temperature and the energy of a black hole, from that one can infer that the black hole has some microstates, an entropy, and a very explicit formula, which I consider to be one of the most important formulas in modern physics, relating the entropy, a statistical quantity, to the area of the horizon of the black hole divided by 4 times Newton's constant times Planck's constant. So this is a formula that relates concepts from across modern physics, thermodynamics, gravity, and quantum mechanics. So it's a central formula. Now, this turns out to be a huge number by any standards. So even a small black hole can store a very large amount of information. For example, all the information in the Google databanks could be stored inside a black hole which is a trillionth of a millimeter across. So the laws of, okay, so they have a lot of information. That's what Bekenstein and Hawking told us. Now, there's something called Moore's law, which you've heard of, just to clarify this, which you may have heard of. So every 18 months, the information you can put into a region inside your computer of a fixed size doubles due to improvements of technology. And this Moore's law has been working pretty well, but ultimately, it will become so small that it will turn into a black hole. Moore's law cannot hold forever. We believe that the black hole is the ultimate, the best that you can do. And it is, in fact, a bound on how long Moore's law can hold, but it's a long, long time. Around 300 years before we have to worry about it. So now, if you were paying attention, you'll realize that I've told you two things which are completely the opposite of each other. One, that black holes are the simplest thing. They are less than empty space. They're nothing. You can't write anything on the surface. It will just dissolve in the middle. They're the ultimate simple object. And yet, at the same time, according to Hawking, they not only contain a lot of information, but they contain a maximal amount of information. So black holes at once embody the simplest and the most complex thing in the universe. And the fact that we arrive at these two different pictures of what a black hole is through two different routes is a wonderful example of a contradiction. We look at it two different ways, and we come to extreme and diametrically opposed pictures of what this object is. So how can we reconcile this? So this puzzle became apparent in 1974 after Hawking's work. And this is what I'm calling the black hole information puzzle. So now enter string theory. And string theory, as I said, is a candidate for reconciling theories with both quantum mechanics and gravity. And if it really achieves this goal, then it must somehow give an answer to where the information is in a black hole. It's obligated to do that. If it can't do that, we shouldn't spend any time, we shouldn't continue to work on it. So string theory began its life, so I'm going to say a few words about string theory, began its life in the 70s with the idea that all particles on closer inspection are actually tiny little loops of string. And these loops can, by rotating and vibrating in different ways, they can disguise themselves as all of the different elementary particles. And this is quite a trick, and it is, it's quite a mathematical trick that one object can appear in these many different disguises. And it's like a guitar string. If you pick a guitar string without your finger on the fret, it'll make one note. You put your finger on the 5th fret, it'll make or the 12th fret, it'll make a note an octave higher. And so just as a guitar string can vibrate in different ways and sound different, a fundamental string can rotate and vibrate in different ways and look different. And those different looks correspond to quite dramatically resemble the different kinds of particles that we see in nature. So this is one of the encouraging facts about string theory. Now, string theory was discovered in the 70s, but since then, it has grown into a kind of network of different interrelated ideas in which strings really directly pertain only to one corner. But somehow it still gets called string theory, even though it's a big network of many different ideas. And I'm going to be using string theory in this bigger sense when I use it to address black holes. Now, there are a lot of beautiful things about string theory. This is not a lecture on string theory per se, but no one will be confident that string theory is the theory of nature until we have some kind of direct experimental confirmation. And since strings are so small, it's not likely that we will get such direct confirmation anytime in the foreseeable future. Nevertheless, we can use string theory as an example of a consistent theory of quantum gravity and try to use it to understand at least one way that this black hole information puzzle can be solved. And then later, as it turns out, we'll be able to generalize that mechanism without relying heavily on string theory. Okay, so in 1996, we actually used string theory, where we have a lot of control over the equations, to try to understand how information was stored in a black hole. This was work with Cumrun Vafa. And we found something very interesting. We found that the horizon of a black hole is kind of like a hologram. And that a hologram is a two-dimensional plate which can project a three-dimensional image. And there's a hologram at the horizon of the black hole that projects the image of the entire black hole. And the fact that the information content was proportional to the area came out exactly of this description, including all the numbers. And this was the first time in the 25 years since the puzzle arose that this formula had ever been, one could ever reproduce it by actually counting some quantum microstates. And so this reconciled the points of view. We had a complete description, and from one approximation to the description, the black holes became maximally simple, and from another they became maximally complex. And to put it more precisely, so I'm not going to try to take you through all the mathematics, but there was some very precise mathematics that came out of this microstate counting that showed that this configurations of the hologram produced by string theory gave exactly what Bekenstein and Hawking inferred must exist. Now, let me describe this in a much simpler way. How can you have two completely different descriptions? Well, this really happens all the time. So it's as if we have two people. Here's kind of the Einstein-Schwarzschild view of what's going on in the theater. They say, this is a very simple situation. There's just one empty seat. And then the Bekenstein-Hawking picture, it says, no, this is very complicated. I've counted all the people, and there's 65. 65 is a complicated number. And they're disagreeing. One says, no, it's simple. The other one says, no, it's complex. And then somebody says, wait, but the theater holds 66 people, and 65 plus 1 is 66. So these things actually agree. Now, in order to understand why 65 and 65 full and 1 empty are the same thing, you just need to know how to add and subtract. But the mathematics that was needed in order to understand how the Hawking-Bekenstein description of a black hole and the Schwarzschild-Einstein description of a black hole, the mathematics that was needed to see that those descriptions were equivalent, just starting from a different point of view, had not been discovered when we started to think about the problem. But nevertheless, it worked perfectly. Now, as often happens in science, the first derivations of this counting of the complexity of the black hole were rather complicated. They involved string theory. But as the years went by, they became simpler and simpler. And ultimately, we learned that it followed from fewer and fewer assumptions. And ultimately, the existence of strings was not required for the argument. And this is really as it should be, because in the middle of our galaxy, there's a black hole, which is 1 million miles across. The purported size of strings is 10 to the minus 33 centimeters. So it doesn't seem right that one should need to understand the laws of physics at 10 to the minus 33 centimeters to understand Sagittarius A star. And the fundamental things that were needed were really largely followed from the Einstein equations, and that's especially so for the extreme Kerr black hole. And science often works this way. You start to answer one question, you may not be able to answer that, you're led to the answer to another question, you assume some things, you learn that you can drop some assumptions. So it's an adventure. We start trying to figure things out, we make some assumptions, and it keeps changing. The game keeps changing as we go along. It's not something where we have a 5-year, 10-point plan. So now let me tell you about extreme Kerr black holes. So it turns out that black holes can spin. And in fact, almost all of them do spin. And there's a maximal amount that they can spin, and that is when the horizon of the black hole itself is moving around at the speed of light. And it's very hard to move at the speed of light, and the ways, or near the speed of light, and the ways that you can do that are few and far in between, which means that these maximally rotating objects, the extreme kerr, the ones that are spinning as fast as Einstein equations will allow, turn out to be simple objects. And there have been 3 of these seen so far, GRS 1915 plus 105. This is the spin of the first black hole ever seen, Cygnus X1, has recently been measured, and it appears to be very near the speed of light. And then there's a supermassive one in a nearby galaxy. So here's a picture of GRS 1915, and the black hole is in the middle here. There's some jets coming out, matter spitting out. Of course, you don't see the black hole. You just see what it does to the matter on this companion star, which it pulls off. It spirals around this accretion disk, and then it plunges into the black hole in the middle. Now, what we want to study is the horizon of this black hole, where the hologram exists, which is the key to where the information is stored. And here's a video that NASA made. So we want to zoom into the center of this black hole, and the hologram, which could explain the microstates, is right in that interesting little spot right around there. That's what we want to study. That is a very special and peculiar region of space-time with some unusual properties. So what happens when you get right in the middle there? Well, you can use the Einstein equation to show that very near, it's a common phenomena in many aspects of nature, including ordinary matter systems, that under special situations, they can acquire extra symmetries. And the extra symmetry, there's more symmetry if we look just at this near horizon region. So away from the near horizon region, there's a symmetry of rotation about this axis. But when we get near the horizon, it turns out that we get much more symmetry. In fact, we get infinitely many symmetries called conformal symmetries. And the appearance of infinitely many symmetries, as bizarre as it sounds, happens in other phenomena in nature. For example, something called the quantum Hall effect, which condensed matter physicists like to study. It has already been observed to happen, and we can use the Einstein equation to show that these symmetries emerge near the horizon of the black hole. Now, these symmetries were the key feature of the analysis of black holes in string theory that I discussed earlier. In other words, we started with string theory, we deduced the existence of these symmetries, and then the symmetries enabled us to understand how the black holes keep track of all the information. So once we have these symmetries, we don't need string theory anymore. And this strongly suggests that this black hole that we see up in the sky, GRS 1915, has a kind of hologram on its boundary, which is holographic plate on its boundary, which is storing the vast quantities of information that appear inside a black hole. Now, I've just shown you GRS 1915, and the other black holes are up in the sky. The Einstein equation implies that they have this symmetry. We can see these things. can we actually see if that symmetry is really there? And we are just now on the precipice, on the threshold of being able to measure such things. And so what I'm going to talk to you in the next 3 or 4 slides before I end here is what we hope to do, both experimentally and theoretically, to put this conformal symmetry on firmer footing. So there's a new telescope being built, which I'm very excited about, called the Event Horizon Telescope. And it's actually has many locations, 3 and hopefully ultimately 15 around the Earth. This is a picture here or a drawing really, of the ALMA array on a mountaintop in Chile. And there's a number of these around the Earth. And by coordinating these radio telescopes around the Earth, they are for the first time in the next few years going to be able to look at 2 black holes, Sagittarius A star and M87. These are the black holes which are the biggest black holes in the sky. They aren't the biggest black holes in the universe. They're the ones that look the biggest in the sky. Sagittarius A star is like 1 million miles across. It's pretty nearby. And so it looks pretty big in the sky. I guess its size in the sky is about the same size as an orange would be on the moon. But these astronomers are really good now, and they can see such tiny things. This is a picture of M87, which is especially interesting for us because it is surrounded by this disk of matter flowing into it, and it has a highly collimated jet coming out of it. Now, the spin of the conformal symmetry is relevant to these rapidly spinning black holes, and neither of these spins have been measured. But it's been noticed that black holes with jets like this tend to be spinning very rapidly. So there's good reason to believe that this M87 is rapidly spinning. And therefore, we may actually be able to see, here's M87 with the jets, the disk around it. We may actually be able to see this region where the conformal symmetry appears. And I've drawn here the different locations on Earth where this is not an actual photograph. The different locations on Earth where the telescopes are located. And we use the different locations to resolve the image. And we're hoping that we may actually be able to see. It depends both on how the theoretical analysis develops and how well the experiment are coordinated, whether or not this will be possible. And now, okay, so that's I've come to the end of what I want to say, but I have to express a little bit of frustration because the really beautiful thing, the beauty of physics is in the details, and how the amazing ability of mathematics to describe the physical world in precise, measurable, and coherent detail. And it's impossible to understand how wonderful it is without actually spending 5 years understanding what those equations means. It's a little bit like going to the Grand Canyon and trying to explain why it's so beautiful without even a photograph. But it's the best I can do in an hour. And again, the thing that is really beautiful to us are, if you understand these equations, it's amazing that we can describe almost everything in the world around us using equations. And it's especially exciting and fun that there's some things that we can't yet describe. And those are the ones that are at the edge of our knowledge, and I've tried to talk about today. So in conclusion, the road to understand nature is full of unexpected twists and turns. We started out thinking about string theory. In order to make sense of that, we learned something about black holes, and we never quite know where it's going to take us next. But and we certainly can't see at this point in time to how we are going to arrive at a complete understanding of nature, or if such a thing even exists. But we certainly can see to the next bend of the road and have many exciting things to work on. So I will stop there.